Hey, ladies and gentlemen, we're going to start with a 3-minute review of what we did last class. First time we talked about notes, we talked about the different original types of models and how they progressed of the atom. Talked about the Bohr model, how we figured electrons moving in and out from energy levels. And then we really focused on the quantum mechanical model that took these energy levels and broke them up into more specific spaces. The energy levels were divided into sublevels, and sublevels were further divided into orbitals. And electrons can still move between energy levels, just like on the Bohr model, and when they do, they're absorbing energy or releasing energy as they move. And we talked about some scientists and talked about light and how light is really a photon. Photon has a wavelength, a frequency, and a speed. And the speed is a constant, but the other two can vary. And we talked about light can be a particle or a wave, and that we looked at this picture. We saw particle and wave at the same time. That was fancy. We talked about the Bohr model, how electrons can change between energy levels, and that corresponds to specific wavelengths of light. And there were emission spectrum that correspond to those wavelengths of light. And I made some analogy about how you could jump up steps and jump down steps, but there's no steps between the third and the fourth step. There's not a 3.5 step. I may have talked about the nucleus as a reference to different planets. Like on planet Earth, you could easily jump from 0 to maybe the third step, but on the moon you could probably jump from the bottom up to like the 12th step because there's less pull. That's similar and analogous to elements. In the nucleus of an element, you have protons that are pulling on electrons, and if you have more protons, you have more pull. Kind of like on some planets, there's more gravity, therefore pulling on your body harder. The ones that have more pull, the electrons moving up between different energy levels would have a different pattern. So every element has its own pattern or spectrum because there's different stair steps that the elements can move around on. And maybe we burned some stuff in class and saw some pretty colors because the electrons were in their ground state before they were burned, and then they got excited while they were being burned, but they have to drop back to the ground, and when they drop back to the ground, they have to release energy, and that energy corresponds to specific wavelengths of light, because again, there's only certain steps that those elements can move to. And we actually kind of see that over here. We see energy excites the electron up, and then that electron has to drop back down and it gives off light. But if this electron can't jump to this spot here, it has to jump right to that energy level. It can't skip the energy level a little bit or fall short. Can't be here, can't be here, because there is no spot there where the electron can move perfectly. Each electron has to move to a certain specific energy level that's dependent on the number of protons pulling on the electron. So they can move back and forth between ground state and excited state. And we got into the wave mechanical model, and we talked about energy levels, sublevels, and orbitals. And we started looking at crazy pictures, and these pictures represent the different sublevels. The S sublevel is spherically shaped, the P sublevel kind of looks like a peanut, and the D is really complicated. And we hopped to electron configurations. And I want to take a second and practice using Aufbau's order with you. So let's take a second and get out the periodic table. And your periodic table on the back has a bunch of things on it. And on the bottom right of your periodic table, there's Aufbau's order. And Aufbau's order is really useful when you're figuring out the order in which electrons build up. So we're going to do the electron configuration for bromine. So let's find bromine on our periodic table. You guys are searching the back of your periodic table, the front of your periodic table, and you found that bromine has 35 electrons? Pretty sure. Let me pause and check. I don't have a periodic table. Yep, there it is. 35. Okay. There's bromine has 35 electrons. Look, krypton's got 36. So pull these two things back up. we have 35 electrons, and we're going to describe where those 35 electrons are. You always start at the beginning, the closest 2 electrons. These 2s, 6s, 10s, 14s, they tell us how many electrons. On the first energy level, there is an s orbital, and it can only hold 2 electrons. And on the second level, there's an s, but it can only hold 2. And there's also, on the second energy level, some p's. There's actually 3 of those p shapes. Each of the p orbitals, or p shapes, can hold 2 electrons. 3 shapes, each holding 2. 3 times 2, they can hold 6. And that also is right there. See, P6, it tells you right there. But you've used up all of the space on the second level, so you go to this third level. On the third level, there's another sphere, or s orbital. It can hold 2. There's a 3p, which is a bigger set of p orbitals. And then keep sliding. Look, don't stop sliding down keep going, and the next thing is the 4s. That's the next thing on this arrow. You can't go to the next arrow until you've used everything on this arrow. So 4s has 2 electrons. Oh, that's the wrong 2. Still the wrong 2. There we go. What comes after 4s? We did 1s, 2s, 2p6, 3s, 3p6, 4s, 2. This is only 20 electrons so far. 2 plus 2 plus 6 plus 2 plus 6 plus 2 is 20. So then we have the 3d. And how many electrons can the 3d hold? Good job. You in the back. 10. Very good. I heard you. That was good. Way to speak up. It's about time. That now gets us to 30. So if this is right now at 30, we have 5 more electrons to account for. So 4p, the 4p can hold 6 electrons, but bromine only has 1 more electron. So 4p6. So that is the electron configuration for bromine. And quite often we will do orbital diagrams, which represent where these electrons are. In the first orbital, there were 2 electrons. I'm trying to draw arrows with a mouse, so be patient with me. In the second orbital, there are 2 electrons also. See, 2, 2. Arrows have to have opposite spin. The opposite spin is the Pauli exclusion principle. Pauli equals opposite spin. Alright, they have to have opposite spin for the Pauli exclusion principle. Now when we come to the 2p, notice that there's 3 orbitals and they're all the same energy. So we would start putting electrons in 1, 2, 3. And now that each spot has the first electron, then we come back and put the second one. And why we're doing this is because when electrons enter these spaces, remember this is space around the nucleus, when they enter these spaces, there's a choice between sharing space and spreading out. And they tend to spread out first. So you get 1 in this orbital, not the best arrow I've ever drawn, 2, 3, and then 4, 5, and 6. So that's the 3p6. 4s2 is next. 1, 2. After that's a 3d. And I know this is out of order. These are all on the third level. But the 3d ends up filling up after the 4s2. But the 4s2 is the 4th level. So that's farther from the nucleus. The 3d10 is the 3rd level, so that's closer to the nucleus. And just the order in which they fill up is not what you might expect. It doesn't go first level, second level, third level, fourth level. It goes out of order, which is why you're given Aufbau's order to help you see the order. D's have 5 orbitals. See, 1 box, 2 box, 3 box, 4 box. How do I figure out how many orbitals something has? The D sublevel has 5, and it's easy to figure out that it has 5. That there's 10 possible electrons, and they can occur in pairs. What is 10 divided by 2 pairs? 5 orbitals. And again, I went and I did up, 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 up. I did my 5 ups. Now I'm coming back and doing the downs. And then we have up, And that spread them out thing is called Hunds Rule. Hunds Rule equals spread. You have to spread them out first. Wait a minute. There's actually 5 electrons. Okay, so I spread them out, and then I'm going to come back and I'll just do these last in red for some reason. So I had to spread out the first 3. Now I'm coming back and doing the last 2. So this has one that's half full, right? That one is half full, and the others are full. And then full, 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 full. What about the 5s2? Well, the 5s2 exists, but it's empty. Right? For this one? So isn't there another one right there? Yeah, 3d, 4p, 5s. There's a 5s, but there's no electrons in there because we used up all the electrons on the first bunches of orbitals there. We will rarely get all the way down here into the 7p6. That would be a whole lot of electrons. Actually, 7p6 would be 118 electrons, which is the new element whose name I can't think of. It's probably a great name. It's probably Murphium or something like that. Who knows? But this was called... so this little review covered a lot of things. First, we covered electron configurations and how to figure out the number of electrons, how to use Aufbau's order, and how to fill out an orbital diagram. This thing that we just did is an orbital diagram. So that kind of covered everything from the first day's notes. So what else do we have to learn? What else do we have to learn? Noble gas configurations. Noble gas configuration is a shorthand way. Instead of having to write down everything, you can write down a noble gas to represent a big chunk. So this is the configuration for argon. Notice that potassium, which has one more electron, right? Let's make sure potassium. Argon has 18. What's that over there? There we go. Potassium has 19, so it only has one more electron. So the difference is slim. So you can see the first 18 and then one more. So they're almost the same. So what people will do is they say potassium is argon with that extra piece. Iron is like argon with these extra pieces. Just like argon, but it's got these extra pieces. You can only do this with the noble gases. Where are the noble gases? Helium, neon, argon, krypton, xenon, radon. So you use these as your reference elements. So if I was doing sulfur, if I wanted to draw the configuration for sulfur, I'd have to use neon because it has less electrons. It would use the first 10. If I was doing, let's pick technetium, which is radioactive element, but anyway, it's got 43, so I could go back to krypton. You could use krypton as the noble gas and then build off of those first 36. And so it can be really useful for big elements. Here's barium. Instead of having to write all this down, you could just write down xenon 6s2. Well, how would I know what xenon was without working out the entire configuration? Periodic table is organized really by this pattern. So keep this in your mind here. Let me get rid of that. Let's actually shrink-a-dink this. Pause for a sec. So I have my periodic table here, and I've got Aufbau's order here. And you can see on the left side of the periodic table goes 1, 2, 3, 4, 5, 6, 7. These correspond to these energy levels. 1, 2, 3, 4, 5, 6, 7. We just did potassium a second ago. Potassium was 4s1. Well, look at this. Oops. Potassium is the 4th level down. See? Potassium 4, potassium 4, potassium 4. It's 1, 2, 3, 4 levels down. How do I know if it's S, P, or D? How wide is this section? Look, 2 elements, 2 elements, 2 elements, 2 elements, 2 elements. S's, P's. Okay, what P's? What about P's? 1, 2, 3, 4, 5, 6. 6 elements, right? 6 elements wide. That doesn't quite work, but 1, 2, 3, 4, 5, 6, 6. D's are 10. Now check this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements wide. So you can, the F's are down here. This is 14 elements wide. So that pattern is hidden right here. So a minute ago I did argon, 4s1, because I knew that argon would be the first chunk. It would be everything up to 3p6. 1, 2, 3 levels down. 3 levels down. It's in the p area, and it's the sixth one. So when I write argon, it's like I'm writing 1s2, 2s2, 2p6, 3s2, 3p6. And then I can just build off of what comes after that. So after 3p6 is the 4s2 and the 3d whatever element it is. So that last example was barium. So we come to our periodic table, find barium. So barium's right here. That's what we do all with. Oh, never mind. Bad joke. So barium's right here. It's the sixth level down. Xenon is just before it, only a couple elements before it. Xenon is on the fifth, 5 levels down. Xenon's a 5p6. So what comes after 5p6 on Aufbau's order? After 5p6 is 6s2. So that's what's going on here. After 5p6 is 6s2. So barium looks like xenon, but it's also got the 6s2. So that really simplifies things for some people. Other people just use Aufbau's order every time. Valence electrons, these are the high energy ones. These guys on the outside are the ones that elements bounce into. Core electrons, all these other ones on the inside. So let's do gallium real quickly. Find gallium on the periodic table. There it is. So gallium's number 31. What noble gas becomes before gallium? Argon. So for this one, we would say we're going to use the element argon. We put it in brackets. And then what comes after that? Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So after the 3p6 is the 4s2. And then the 3d10. And then 4p1. And I do that in my head, but you don't have to. Let's look at the periodic table. Gallium is right here. So we have the 4s2, 3d10, 4p, and it's in the first column, so 4p1. So they're all like little addresses based off their position on the periodic table. New stuff. So a little bit of history again. We've got a lot of history here and there. Dmitri Mendeleev, that's this guy here. That's a fabulous beard. Hashtag beard goals. This is his first version of the periodic table here. He's organizing them by groups, by how the elements kind of go together. Fluorine, chlorine, bromine. He's got manganese there, which is a mistake. Oxygen, sulfur, selenium, tellurium. He's got some mistakes there too. And this is one of his first versions, and he slowly gets better and better. Look, he's got lithium, potassium, rubidium, cesium. Those guys are all in the modern periodic table. Lithium, sodium, potassium, rubidium. It's a pretty good job, Dmitri. And he figures it out. He puts it together. He's got a couple mistakes. But the big deal is he predicts some things no one else had ever seen before. Predicts some missing elements. Let's see if we can find... Oh, right there. Like, he's got nothing for this element, but he knows it's got to be there. And he's got a couple others that he predicts. And he doesn't just predict that they exist. He also says what they would have, what type of properties. Mendeleev, his periodic table is improved by Henry Moseley. Henry Moseley does atomic number. Now, there's some controversy as to who really came up with the periodic table, because a whole bunch of people are working on similar ideas, but Mendeleev is largely given the most credit, because he doesn't just put them in order. He comes up with reasons, he comes up with predictions, he comes up with a lot of facts. He has a couple mistakes because he goes by atomic mass, but that's just because no one knows anything about protons yet. Once that is all figured out, the mistakes are fixed. Nowadays we have names for these different groups. Your periodic table is numbered 1, 2, 3, 4, 5, 6, 7, all the way to 18. And I think we already wrote these down. Alkali, earth are the first two. Transition is everything in here. That's the D area of the periodic table. The nitrogen family, oxygen. Halogens is group 17. And the noble gases is group 18. Periods run this way. That's horribly drawn. Sorry, mouse work here. So this is the 5th period. This is the 3rd period. This is the 15th group. This is the 4th group. And so that's how the periodic table is organized. So if I said, what element is in period 5? Group 14. You go period 5, group 14. Hit that spot right there. I can't do that in my head. 5, 14, 10. It's the element 10, SN. So it's not too hard. What about ionic size? Let's talk about ions again. Remember, if it has a negative charge, that means it's gained electrons. If it has a positive, it has lost electrons. Nice spot. That's a great spot to write. There we go. So if it's got a negative charge, it's gained electrons. Well, what would happen to its size? Well, if it is -2, it's larger because it's gained 2 electrons. So if you go from sulfur -2 versus sulfur, sulfur -2 would be larger. What if it's positive? Well, if it's positive, the one that's not charged would be larger, because once it's positive, it loses electrons. In the case of calcium, calcium is 1s. Let me see if I can write it all out here. 2s2, 2. That's not a 2. 2p6, 3s2, 3. Oops. 6. Nope. 6. Dang it. I can hear you enjoying that. I'm going to change the last one to red. There we go. For a very specific reason. So calcium is this. That's calcium. But when it's a +2, it's going to lose these two. The last two. It's going to lose, well, again, what we call the valence electron. Those electrons are the farthest from the nucleus, so they are not pulled on the nucleus as strongly as the rest. So that's where the action happens. Those last couple of electrons on the outside, you could think of an atom and its electrons like an onion, because the onion's got layers. You know, and you peel the outside layer off first. You always have to peel the outside layer off first. So the 4s is the outer layer of this onion. That's what you peel off first. Yes, that was a Shrek reference. Donkey reference. Yeah. Shrek. I don't know. Periodic table. That's beautiful. Okay, a couple of things about the periodic table. People often look at the periodic table and come up with different trends, things we've observed. We're actually going to skip ionic and go to atomic size, because I think this is the most important trend. So when we look at the periodic table, if we compare two elements, say this element to this element, one of these elements is going to be bigger in size, like the onion is bigger. Well, which one would be bigger? The one that has 1, 2, 3, 4, 5, 6, not quite enough space there. Let's increase the font size to make it work. Nope, too big. That's pretty good. There we go. That's darn close. So it looks like X has 4 layers versus Y has 6 layers. So which element would be bigger? If you said Y, you're correct. Merely because it has more layers of electrons. As we go down the periodic table, atomic size increases. Now, this other one confuses people. As we go across the periodic table, from right to left, atomic size, well, from right to left? Who does from right to left? whoever goes this way. Huh. I usually always go the other way. So if you go from this side of the periodic table to that side, then it increases. Ink. Most people don't think right side to left side. Most people think this direction, because that's how we're taught to read. And if you think that way, like I do, then you would probably say decreases. Why does it decrease as you go to the right, which is the same as increase as you go to the left? As you move across, this is all of these elements. Here, let's pick the highlighter. I never use the highlighter. All of these elements are on the 4th level, so they all have the same number of layers of electrons. However, they each are gaining more and more and more protons, and those protons pull the layers in. So those protons pull the layers in. When you get to the right side, there's a lot more protons that have pulled the layer in tighter and tighter and tighter. So the size decreases as we go across. There's a term for that. It is called effective nuclear charge. The nucleus is pulling the layers in. Why does it get bigger as we go down? Because we added a new layer. So it gets smaller, smaller. It goes big, smaller, smaller, smallest, new layer. So big again, and then it gets smaller. And we see this trend over and over again. This trend of size can be used to help understand other trends. Like say we were trying to remove electrons. Would it be easier to remove from element X or element Y? If I wanted to pluck an electron off, which one would be easier, meaning less energy? Probably Y, because it has more layers of electrons. And that's the case, which it's actually the trend is the inverse of size. So I'm going to go back to the ionization energy trend. Ionization energy is energy to remove an electron. So before, now the electron has been removed. See? It's no longer attached. So we have a similar periodic table down here. As we go down the periodic table, again as we go from, let's see, element, this is sodium Na to cesium Cs. That was ugly. As we go down, we're gaining more and more layers, so it gets easier and easier to remove. So most people look at it as you go down. This again is written opposite of the way I would think about it. It says increases as you go up. As you go up, it increases. As you go down, it decreases. I usually think from the down perspective. As we go across, it increases. Why does it increase? Because I keep getting increases. As we go across, because there's more protons. That's why it's increasing as you go across, because there's more protons. It decreases as you go down, because there's more layers, more energy levels. Shielding effect. What the heck is shielding effect? So let's draw. We got. Oh wait, I can use circles. Here we go. First, we got the nucleus. Let me pause this. I'll draw quick. All right. So this is the nucleus, and this is our first energy level of electrons. And then this is our second energy level of electrons. The nucleus pulls on the electrons and pulls on the electrons. Yeah, both pull by the nucleus. But what is this layer of electrons and that layer of electrons relationship? It's repulsive. Yeah, electron layers don't like each other. This electron layer is moving around, boom, 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 and it is repelled by it. If I add another layer, this layer is going to be repelled by both layers. And you could see like there'd be some shifting. And then this would shift back, shift back, shift back. And that layer, freaking you out, man, that layer would be repelled. as we add more energy levels, there's more repelling from the inner. The shielding effect is where the core electrons, these layers on the inside, block the valence. The valence is the outside. So this, right now, the third level is the valence for this element. If you had a bigger element, now this one has 1, 2, 3, 4 energy levels. So it might be calcium. 1, 2, 3, 4. Calcium has 4 energy levels. So the outside layer is repelled by all the inside layers. You can't get in there. That's blocked by them. So it's still attracted to the nucleus, but there's way more repelling. So as we go down the periodic table, since we have more energy levels, we have more shielding effect. What about as I go across? No change. As you go across, all of them have 4 layers. Every element in that period has the first 3 layers completely filled up, and it's just the 4th layer that's changing. Boom, 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 boom. Whether it's calcium here or argon on the other side, it's 4 layers, 3 that are repelling, and the 4th layer that's being filled. So no change. Electronegativity is my brain just lost it. It's a pull on electrons in bonds. And so when we look at the periodic table again, we see the same relationship between size and electronegativity. This is a little bit weird though, in that I'm going to say bigger is weaker. Big equals weak. Small equals strong. What do you mean by that? Good question. So again, if you, let me steal my numbers from earlier. So these energy levels here correspond to how many layers there are, right? So if an element has 4 layers, which those don't quite match up, it's going to bother me. The inner layers repel the outer layer, and when that element tries to bond, it's like you're adding to the outside layer that's being repelled. But what if you're 6 layers deep? There's a whole lot of repelling. So as we go down, they don't pull on electrons and bonds as much. As we go across and the size of the atom gets smaller, they pull more and more and more. The strongest elements are the halogens. They pull on bonds really, really, really strongly. Wait, why not the noble gases? The noble gases don't form bonds. They already have everything sorted out. In fact, it's ridiculously difficult to make noble gases bond with anything. Polyatomic ions, here's a picture. That's pretty funny. Okay, that's the ends, notes, part 2.